Okie dokie. So, ready to go again. I need my black marker. And off we go. So, some more people show up. Homework, you get it posted today, tomorrow. I'm just trying to refine something. The ideal goal of life is to actually get you something where you have to start using that simulator here, which looks like this, with an owl, which is kind of fun. Oops. What can it do actually? Can it move? Yes, it can. Okay, fine. It's just wiggling around. Problem I'm still having at this moment is when I let it go, it falls over. I just need a few more tunings before that works properly. I will make this thing available very shortly, since it's also part of the project. It will run under any form of Unix system, but not any form of Windows system, since we don't support that. So you can always run it through our computers from this account which we have for you. But you will get installation instructions how to install it on standard Unix computers. It doesn't require a lot of libraries. It's very lean. And it has everything which you need in order to do something more interesting. So we'll see. So this is essentially also what should be the interface for the real now robot. We're working on that, and I hope this will all work out so you can interface through this interface directly to the robot and have a more control-like interface rather more like a toy-like interface, which we currently have. Okay, let me get rid of frying the CPU on my computer and get started with a add-on topic. So we have pretty much done with nonlinear control. Linear control, nonlinear control, modeling of systems. We talked a little bit about planning the last time. Planning is critically important, and very quickly we spend a lot of time with planning, on planning, when you do more complicated robot tasks. And then planning and nonlinear control together become actually a complicated loop to optimize over time. One component which I just want to spend one lecture on, essentially. Many things which come right now is like these one lecture things. I want that you know a little bit about certain topics. Without that, I can tell you all the details about it. And one of them is essentially what is called interaction control, or force control. And you could take this entire course and start it actually in a different way. You could actually take this course and say, if I have a robot, make it a human-like robot, really all that matters to us all the time is how we interact with forces in the environment. And obviously there are different forces, so let's give them some numbers. And that is really what is the most fundamental thing, that we are interacting with the environment puts forces on us, and our body and motors and control system has to do the right way of interacting with the environment. It's surprisingly easy to just create a robot which is mounted to a wall and just has two moving arms without touching a lot of things. This is essentially what you've learned so far. It's very straightforward to work with. The moment you start touching things, things become way more complicated. One of the things is that often you don't even know how the environment is going to react to you. Is it going to be soft? Is it going to be stiff? Is it going to be, I don't know, spongy? Is it going to be just viscous in a particular way? These are things which are actually surprisingly hard to model. So you've seen rigid wire dynamic models. There's also something which is called friction models or interaction models. And there you go quickly into finite element analysis and really complicated procedures in order to model it. And even then, it's not very accurate. Or if it's accurate, it runs forever on a computer, so you can't really work with it anymore properly. So the entire topic of interaction forces is quite interesting. when people started to do this, so the traditional approach in robotics in the 70s, 80s was to have big robots with big gearboxes. You will hear more about gearboxes and transmissions actually very soon. But the key was that they were very stiff controlled. They had usually negative feedback controllers with very high gains, no feed-forward commands, no nonlinear controllers. And that means they're like stiff like a rock. If you push them against them, they don't give in at all. They're really, really stiff. And then if you have a stiff robot like this touching an object, well, there's essentially two things again. Either you destroy the object, or you stay above it, or you just plan and control really accurately that you go along the surface. But that becomes actually surprisingly hard, this level of accuracy. And if you don't do it right, then you suddenly have the PD controller really hard pushing against the whiteboard, for instance, and you start what is called chattering and all kinds of vibrations, potentially destroying everything. So these kind of stiff controllers are really useless for interaction control. And you need actually model-based controllers and soft controllers to do that. And I just want to show you a little bit about some basic, very simple examples of force control, and in the end just hint at how this is embedded in the bigger controller. So you get at least a feel for that. Again, some people would say we should teach robotics completely from the viewpoint of force control and develop this entire topic like this, which would be useful, but that would be a real purely controls class. It would not focus so much on kinematics and modeling and how to deal with a robot and all the kind of computations you have to do to work with a robot. All right, so I'm going to talk about all these little things here: compliance, impedance, force control, hybrid control, impedance control. Forget about sensors and actuators. We'll do this the next time. We'll just focus on this peacefully today. So let me give you a fun example about force control. That is this guy. So that is one of these Puma robots, Puma Unimate robots. I showed you that very early on in the first lecture. A robot which was basically developed in the 70s, 80s, and which was one of the most common industrial manipulators at this time. Very clunky, like 200, 300, 400 kilograms heavy. So this is actually happening at Stanford in Osama Khatib's lab, like 20 years ago, most likely. Mounted on a mobile platform so that it becomes mobile. So that whole setup most likely is by now 400 kilograms. And so it's heavy, really big and heavy. And it would by itself not want to give in. You run into it, you run into 400 kilograms, you know, that just the 400 kilograms win, I promise you, for most of you, unless there's some sumo wrestlers here already. And then basically people worked on creating force control interfaces to this robot, and this is essentially what came out of that. Is essentially cool. So make the 400 kilogram bastard become a gentle dancing partner. No clue whether male or female, just robotic. And this is quite some work, since basically what you have to do now is you create interfaces where the robot can sense the force loop and give in. That means if you could do stupid things, you know, you could just go and shake this thing, and maybe it starts pushing back and forth against you. It has some delays, it may just explode. So it is, what the guy is doing in this moment of time is relatively bold, and most likely would not be recommended and not be sanctioned by any kind of ethics board at a university. Then you could have been killed if something was wrong. But still cool. I guess he was the guy who programmed that and had deep, deep confidence in his skills. So let me go and tell you a little bit about force control. Now, what happens the moment we interact with the environment? First of all, so if you really think about the model, we touch something, we get suddenly a closed loop kinematic system. So it's not an open branch, an open chain anymore. It becomes closed. The moment I touch something, this here through the environment becomes a closed loop. That makes actually our kinematics and dynamics different. And you have to do something to model them appropriately. You get motion constraints from the environment. It is obvious, so you cannot just push into the table. This is not going to work anymore. So you have to plan and you have to control appropriately in this direction, while in other directions you don't. So you actually get some differentiation suddenly in which direction you can do what. Which also means you have to know about the environment annoyingly. Essentially what you would like to know is the normal of the surface you're pushing against, since in the direction of the normal you can't push properly because there's a constraint. In the tangential plane you can, and everything remains as normal. We will get back to that at the end. So if you do planning and execution, if you only do motion control, that means just kinematics, then you have to be really accurate. This is what I described to you. You just want to go along this whiteboard, and I do this purely without feeling something. It becomes really complicated. It's actually very cool. The humans are incredibly dependent on force feedback. People have made little experiments. I should actually brought the video. It's about a person lighting a match, okay? Each of you can do that. Now what you do is, everybody can do this, you do have vision and you feel the match and you just swipe it and light it and it's all fine. Now you anesthetize just the skin of the person, the manipulating hand. People can't do it anymore. It takes them forever. They break at least 20 or 30 matches before they can light it. So the moment you lose your tactile sensation, your force control, you're actually getting severely handicapped. It also turns out that we get a lot of feedback from your feet, whether you notice or not, I have no idea. And if I anesthetize that, you fall over all the time, totally. And that's actually, unfortunately, in some older people, a disease. And then people have tried to figure out, what are we going to do? How do we help them? Actually, they created something like vibrating shoes, which enhance the kind of tactile stimulation, and that helps them to balance again. So forces matter tremendously in our daily life. Just we don't notice how easy we use them. So fine, if you do only kinematics control, you would need extremely exact models of the robot, of the environment, so that you just scrape along the surface. That's not really what's the right thing to do. The right thing is to do something like force control directly. We need a new control variable, which is not position, velocity, acceleration, but which is force. Good. Some terms people like to use. Many of those you know, some of them you don't know. Stiffness. Stiffness you know from good old springs, okay? Force equals a stiffness constant times the delta x something has been pushed away. So it comes from this old spring model, which everybody knows. Just simplicity, let's use it again. Here's my spring. It's attached against the wall. And let's call this position here x. And then this is the rest position. If you now basically push it to another position, then you have this delta x. The spring has a spring constant pi, and F equals delta x times k. Okay? That's the force which you're generating this moment. People like to use the word compliance frequently, which is nothing but the inverse of stiffness. So it's 1 over k, just turning it around. One is how much something basically resists to. The other one is basically how much it gives in. Both of them mean the same. There's something which is called active compliance or active stiffness versus something which is passive compliance and passive stiffness. And this is actually pretty straightforward to understand. So all you are essentially passively stiff mechanisms. So your muscle system is squishy. So I can push you and you give in. This spring here would be passively giving in. I don't have to control anything. But this is not at all the case in most robotic systems and control systems. So many systems we have are hydraulic systems. Hydraulics, we'll see more about this. But essentially, you can think about it very simple. There is something like a piston, and it has hydraulic fluid in it. There's something attached to this thing, like this, and then this creates a force, F, and you pump essentially fluid in here, or you pump fluid in there, and then the piston moves back and forth. Very straightforward. But oil turns out to be an incompressible medium, to the best of our physical interest, let's put it this way. That means if you push this thing back and forth, it's great. But there's no compliance at all. If you push against it, it's nothing. Okay, try this perfect experiment. You see is the optimal playground. Just find an excavator. There's always excavators here digging something. and just push against the excavator and see whether it gives in. They're all hydraulically actuated. And you will figure out, no, they don't give in at all. They're stiff like a rock, and this is what hydraulics does for you. And in order to basically make it compliant or give it some stiffness properties, you actually have to put something like a little load cell here, something called a load cell, which measures the force. And then you can basically take this here as feedback, run it into something, so let's call this F measured. And here's something like F desired. You compare this is plus, this is minus, and then you kind of correct with your motor control input to the system. And that becomes now an active regulation. And it's done actually, we have a bunch of hydraulic robots which is done, it's also done in robots which have gearboxes. You will hear about that gearboxes may actually actuation the same stiff as hydraulics. In order that the system can give in, you need to have this active regulation in a very, very high frequency loop, usually on the order of 5 kilohertz, to make the system behave as if it were giving in. It's a stupid concept if you really think about it, since you now have to spend energy to give in, while this thing would give in for free. The nice thing is you can actively change the stiffness here, which you cannot in a normal spring system, since it's just what the spring is like. Now, people actually work a lot on motors which have inbuilt springs and which allow you to somehow regulate the stiffness of the motor. Fine. Active compliance is controlled compliance, actively giving in. It's in most interesting robots these days, just not in industrial robots. All humanoid robots, for instance, have components of active compliance. Everything which is somehow out and tries to interact with a normal world has active compliance. Is compliance important? If you cannot give in, you're too dangerous or you break yourself. So passive compliance is fine. So muscles, tendons, whatever. Also some bending can do that automatically. Last thing is what is called impedance. And that's just a generalization of stiffness as you want to. So stiffness here is just basically a static component. So if I basically deflect this by delta x, it does something. But if I basically try to move it from here, there's a process of moving it from here to there, then I will also feel the mass of this spring, and I will potentially also feel some kind of friction components in there which come from velocity. The mass I feel with acceleration, the friction I feel due to velocity. So these terms are also there. So people call this entire thing then impedance. They basically the acceleration properties, the friction properties, and the stiffness properties, usually modeled as a linear system. That is the complete force you need in order to move the system around. Again, this is a fun example if you want to do that. You can go on the weekend to the Queen Mary in Long Beach and try to push it away. It would actually work if it were not anchored in the ground in a very solid way, unfortunately. But you can actually go and push a really, really, really big boat away. You can see this whenever you take a ferry or whatever. People can actually push it away. It's slow, but it gives in. What you get is a huge amount of basically impedance proportional to the mass. So the thing is heavy like hell. You get some viscous friction from the water, but you have no stiffness because there's no stiffness in the water, which is very relevant. So it's a typical example where suddenly the inertia and the friction is very noticeable. Good. So many people then in the end say, what you really want to do is impedance control. And what this video was showing you, it was a dynamic movement all the time. It was doing impedance control. It was trying to make the robot behave like another physical system. And that's really what it boils down to. The robot may be, I don't know, 1,000 kilograms heavy, but I could just say I want it to be behaving like mx double dot plus bx plus k, and I say m equals 1 kilogram, and b equals 1, for instance, and k equals 1, 2. I just like 1 because they did it right. And then basically I simply prescribe, I want, when I move my end effector, which is somehow characterized by some x double dot, this should be x variable here, and here should be x as well, to be precise. I want it to behave as if it were a 1 kilogram system with very little viscous friction and a little bit of springiness. And you can make the robot to behave like that. And this is what the guy did. He made the robot behave like a friendly point mass. Most likely not 1 kilogram. He made it most likely a little bit more, like 10 kilograms. A little bit of friction. You need some friction. If you don't have this, you don't dissipate energy. You always want to lose some energy. Most likely he had no stiffness term since he was just wheeling it around. Makes no sense to have a stiffness term in there. But that's essentially what he was after. Just make the robot disappear and behave like a much lighter and much nicer system. Again, totally perfect. Sounds great. We can do this theoretically, as you will see. In practice, this can become hell dangerous. If that is a 1,000 kilogram robot behind it, then the motors have to work like hell in order to make a 1,000 kilogram system behave like a 1 kilogram system. And one mistake, and it will behave like a 1,000 kilogram system going wild. And it's not fun. So whenever you do force control, things become a little bit more exciting in the lab, particularly with a big robot. So what I would like to do is I want to develop very simply a force control law so that you see how this works, what it feels like, what goes into that, and it's going to remain super simple, as you will see. We just do very simple equations which we manipulate back and forth just to give you a feel for what this sounds like. Okay, so let me just replicate that picture since I'll refer to that for a while. So we have a wall, then we have a spring, then we have a mass, and we have a force pushing here. We measure simply x from the point where the spring is in its rest state, so we can I could write delta x all the time. It's just and we assume this has a spring stiffness Ke. So this is a super simple model how we imagine a mass pushing against an object. Obviously, between the object and the whiteboard is no spring, but the properties of the object and the whiteboard together give some springiness thing. So very easy. Your shoe soles actually are kind of a nice spring. They give in a little bit, not too much, much more than me punching against that. Okay, so this is just a model of the environment. Most environments are pretty stiff, like this here. Doesn't really give in a lot. I don't notice my fingers, my skin gives in mostly. I don't think the whiteboard gives in. Okay, so let's try to. What we want to do is we want to essentially given some desired force, potentially also desired force velocity, desired force acceleration, if you want to. Okay? And we would like to realize that force as much as possible. So we basically want to push against this and realize this force if desired. See how hard this is. Okay, I go and try to get this all going one by one, just to see equations here as well. Fine. So this environmental force, obviously, F environment equals x times Ke. So that's straightforward. And again, I don't do delta x because I measure x just from the response. But otherwise, it would be delta x all the time. Now, equations of motion of that simple thing, we know it is just some F equals mx double dot plus kx times x dot. Is there a dot missing? No. Ke times x. No. No friction. We didn't put a damper in there. And then there might be an unknown disturbance. Did I have this picture originally? I should. Yes, just I forgot. Here, this arrow is some disturbance. Okay? I don't know what it is, where it comes from. It's just more. It just accounts for everything I don't know. It's kind of nice. Okay, so these are my equations of motions. But now I want to reformulate them in what I care about. Actually, I care about forces. Okay, I do not care about positions and accelerations at this moment. So what are we going to do? We know Fe equals x times Ke. That means we can also Fe dot equals x dot times Ke. And if I wanted to, Fe double dot equals x double dot times Ke. Okay. So let's replace things appropriately. So F equals m now x double dot becomes Fe double dot times 1 over Ke. Then Ke times x dot, that's the environmental force plus F disturbance. Okay, if this looks pretty much like this equation. Perfect. And it's also useful to define an error term. Just error at force is going to be F desired minus F, minus F environment. Okay, cool. And okay. And now we need a control law. So what we want to do is we want to create a force here, or a control law for the force, such that in the end this error becomes 0. That means the environmental force is equal to my desired force. Cool. So how do we do that? Well, we do this the same way as you did your homework. We basically try to cancel all the model terms. So here's kind of the attempt to do that. So what do we know? We basically say, how did I do this? Okay, I did m over Ke, and I pulled this out of the equations. Okay, so and then I have Fe double dot. So what do I put in for Fe double dot? Well, I can, but here, in my control law, sorry, this is the physical system. I just basically create a control law where I try to cancel all terms which I know. So what I'm going to do is, I guess, give a desired double dot. Then I give a kind of velocity gain in force, so a kind of force derivative gain times E dot F plus a force proportional gain, EF. And I add in here plus Fe plus F disturbance. Okay. So important. This here is the system model. This here is a control law. Okay. This here, what was the rationale? I basically create a control law which hopefully cancels Fe. Since I want to basically take this F and plug it in here. Okay? And then it should cancel Fe and F disturbance. So these two things. I can just try this out. Let's just basically write it out. Let me see where I have enough space. I can still do this here, I guess. So I get essentially M Fe double dot over Ke plus Fe plus F disturbance is the entire thing here. This is M over Ke times F double dot plus Kef times E dot F plus Kpf times Ef, okay, plus Fe plus F disturbance. Okay? Fine. If I have this, now I accomplish my goal. This here cancels against this. This cancels against this. So I'm just left with this term and this term. Now let me go to the top. I don't want to get rid of all of this. Let me I want to keep the system model around. So let me just write this high up. Okay. So I can now get rid of this. And just basically summarizing what I'm left here is M over KE FE double dot equals M over KE times F double dot plus K. Well, it's essentially just a PD controller in force space. Nothing we haven't seen, just we haven't applied it to the idea of forces. Okay, now I can cancel those terms as well. I can bring, this is F desired here, I can bring this on the other side, which gives me essentially F desired double dot minus FE double dot equals 0. Okay. And we realize that this is equivalent to E double dot F. Now we have an equation which says E double dot in force times some velocity term times the velocity of the force error times some K term times the position of the force error, and this thing has to be 0. So I can write this out one more time. Equals 0. Now, what's the equilibrium point of this? Something we've thought about now. The equilibrium point means the dots are 0. So, fine, kill that. That means we have KPF times EF equals 0. The only way this works is that our error goes to 0. So that's why we like these kind of error dynamics, which look like simple second order systems. They equal 0, and then we know they will converge to 0 automatically. This is the only solution that the system has. It only converges if those constants are chosen correctly. If you choose the gains too high, you will just diverge. That's just a stability argument. But normally you will converge. Okay, so this is kind of approved. This is a good controller. Perfect. Nothing to worry about. Okay, so this is what this showed. This is all pretty, except it doesn't work at all. It's totally nonsense. That's fine. So why is it not? Let's get rid of this and start all over. My controller is still useful. I want to keep this. So aerodynamics can go away. Let's see. So what problems we have? First of all, we assumed, so you have to put this back in here, plus FE plus F disturbance. Okay, that belongs to the controller. So we assume we know the disturbance, but the idea is we don't know it. It's something which is unknown, it's our unmodeled stuff, so this is not given to us. The other thing is, what is annoying is we are basically dealing with force derivatives here. Now, if you ever looked at a force sensor, then you just show you a plot over time. So this is the force over time. This is what you measure at a constant force level. And this thing looks like this. So usually with quite some high amplitude noise. That's just a process of measuring forces. It's not a very clean process. If you take the derivative of this thing, you get an even bigger mess, so a numerical derivative. If you take that and you come back to that at some point, you filter it on top, then you get delays. And in force controls, delays are even worse than what I showed you with delays or discrete time systems before in linear control systems. If you try to for force control with delays, you explode really, really fast. So it's like essentially this guy dancing with a robot. Let's assume the robot has like half a second delay before it feels the force. Like he pushes, the robot half a second later pushes back. Then he's afraid, and then they start pushing back and forth, and the thing just goes wild. Okay, good. So let's essentially, so these are the problems of this controller, but the first thing you can basically try to figure out what happens if you don't know the disturbance force. So we have to eliminate this term from the controller and plug it back in there. So we do the same analysis as before, but the disturbance force is not canceled. And what you get essentially now is for this aerodynamics, same as what we had before. But, so this is PF times PF. It's not 0 this time. It basically is equal to KE over M times F disturbance. Okay? That's your new aerodynamics. Again, you now, what's the equilibrium point of this? Well, you set the double dot, the dot term to 0, and then you're left with this. That means there is a final error, EF, left. That is really what is important. So we can look at this for a second and get this EF, if you solve it, equals KE over KPF times M times the disturbance force. The annoying part now is that usually KE, as mentioned, is really stiff. That's the environment. So it's a very big number. It's not just one, it's like 1,000 or 5,000 or whatever. So now you have a big number here. You have usually a finite gain. You cannot get your gains in a proportional controller so high. So that is usually does not go so high. And depending on the mass is, I don't know, let's assume it's a kilogram right now, so it's just 1. But usually you get a big number divided by a smaller number. That means you're amplifying the disturbance force significantly. And that's quite annoying. So you don't want to do that normally. So this controller is no good. And yet now you can start fixing it. And now is essentially where you get into, in control, you get into these iterative processes where you have an idea and try things and so we'll see what works out. So one thing which works out is actually the following idea. We modify this controller. And then here we have plus FE. And now we do something silly. We say plus F desired. Totally different concept. And see what happens then. Cool. So we can do the same thing. We plug this back in there. So we can do this game one more time completely. So we have M over KE, FE double dot plus FE plus F disturbance now equals all of this. M over KE F double dot desired plus KEF E dot F plus KPF EF plus F desired. Okay, now let's see what we can do. Now nothing cancels so beautifully and easily anymore, unfortunately, as we had it before. So FE and F disturbance and all that stuff is still in there. So let's just try to solve that. Now we bring FE over there, so that we get F desired minus FE, which is our error term one more time. So that's one useful thing. So this one goes over here. Negative sign, I can then replace this here with EF. Okay, so that was nice. I can bring this term in here as before. So that allows me to write, take this one out and write E double dot F. Okay, and now I can solve basically this equation and bring everything which I don't have on this side on the other side. So fine. Let's take, I want to basically the aerodynamics uncontaminated, so I can take this EF term on the other side, for instance, and this term on the other side, and then I have my aerodynamics written again. And we should get something which Well, it's actually not useful. Okay, fine, take this back. Not yet. We have to bring this thing in here first, because it has the same EF term. So we can do MKE times E double dot F plus KVF E dot F plus then EF times KP. And then if we bring this in here, this becomes KE over M, because it's pre-multiplied by this term. And this is still our F disturbance. Okay, and now we can write the aerodynamics. So I basically have this equation here with KE over M on the other side. I just bring it on the other side. And we can write the final aerodynamics, the steady state error, if we do equilibrium point analysis, to be 1 over, what is it? KPF M over KE plus 1 times the disturbance force. Okay? Now, what is nice about this suddenly is now KE is in the denominator here. If KE is really big, which is the case in most problems, then this term here potentially goes towards 0. So we can actually start ignoring it. And we get essentially a remaining error which is proportional to the disturbance force, but not magnifying the disturbance force anymore. Well, it was proportional before, but it's not magnifying it. It's basically something which is smaller usually. Okay. And that's a huge improvement if you want to basically execute that. So that was now basically using some interesting intuition study equations, putting a term in there which was not entirely intuitive. Just after you go through the analysis, you actually see what was happening. Cool. So this is definitely a better control law, and we can still make it better. And one is to avoid derivatives. And the idea is, instead of using the derivative FE dot equals x dot times KE, if you can measure x dot, which is usually much easier to measure, since we can, for instance, compute x dot from our joint position center, if x refers to the n effector, then we get a much, much cleaner signal for velocity. So we would not use the force. We would use x dot times KE rather, not the force derivative, we use x dot times KE rather and get a cleaner signal. So what's our control law now? Let me clean up a little bit. Go back to the control law, F equals M over KE. It was times F desired double dot. Originally, then it was times KVF times E dot F plus KPF times EF plus F desired. So that was our recent control law. Now we try to get rid of this term here. Basically replace EF with F desired dot minus x dot times KE. So this here replaces this term. F desired dot is not so much a problem, so it's a plan. That should be clean. There should be no noise in this signal. Okay, so we have this plugged in. And then we can say, okay, most of the time you really don't care about the transients when you're touching the system. So the acceleration of force and the velocity of force are not planned. They're actually meant to be 0. You just want to go touch something and have a desired force, but you don't have a plan for the acceleration and the velocity of force, so to speak. If that is the case, then this here would be 0, and this here would be 0, and our control law becomes even simpler. So we get now minus KV times x dot, we get KPF over KE, and so it's now basically multiplying the KE in there. Let's just do that. So we replace this term here with minus x dot times ke. Perfect. Now we can take the ke in there, then it cancels this ke, and we get the ke in here. And that is kind of our final force control law. So we just look at the velocity of the end effector, we look at the ratio of kpf over ke, we have a force error which we somehow need to measure, and the desired force. So it's a much simpler control law, it's much more realizable, and you have not heavy-duty noise components. You do need to know, you have to at least have an estimate of the environmental stiffness, which is not necessarily trivial. And people basically created adaptive control algorithms which automatically estimate these things the moment you get in touch something. We talk a little bit about adaptive control at some point, how things like this work. But this becomes a reasonable control law you can work with, essentially. Cool, very important. You start from our basic knowledge, that is, we start with we know PD controllers, we just put them into force space. And then we analyze our control law and basically see what goes wrong. Again, the stability analysis, equilibrium point analysis is always very critical in that. And from that you see, okay, this didn't work, this doesn't work. And this is how all this stuff is developed in the end. It was never developed like, oh, magic bullet, I know what to do. It's always iteratively, this didn't work, people try it out on a real system, and at some point they converge to something which seems to be reasonable. Originally it was all research, now we know how to do it. Good. Now let's put all of this into a complete control law. We were just in that very simplified 1D world, but we know how to actually do these kind of simplified worlds, if they happen at the end effector, and put them into a big nonlinear control system. So let me get rid of this. Don't need this anymore. We assume we have just our control law. You can figure all this. And what matters is essentially our big old friend, the rigid body dynamics. E of q, q double dot, plus c of q, q dot times q dot, plus gravity of q equals u. And this thing changes if there are forces from the outside world, plus Jacobian transpose times those forces, which depends on the sum. Remember the story about the Jacobian transpose? So the simple picture was this. If this is your simple robot arm and you're pushing here with a force, what is the torque that every degree of freedom has to generate in order to hold out against the force? And it's just this force times the moment arm to this degree of freedom, which is F cross product with this moment arm, let's call it, I don't know, A1. And in order to figure out what's the torque I need here, same story, this force, now this becomes my moment arm. So this here becomes A2. F cross A2 is the torque which I have to generate, so this would be here. Q1, no, sorry, it's not Q. U1, U2, etc. Now it's basically, if you remember this, this is how we basically define the geometric Jacobian. Geometric Jacobian is just modeling exactly these kind of relationships. That's why the Jacobian transpose times force, just repeating that, tells me what torques to generate to hold out against that force. It's just statically holding out. So the moment you have interaction, you always get the rigid body dynamics equations which look like that. Cool. And if you want to create a control law now, fine, you can do an inverse dynamics control law. This is basically written here. Maybe not write this again. So U equals B of Q times some Y. And this Y is called some reference acceleration term or whatever in the book most of the time. And you can instantiate that, but let's ignore it for a moment. CQ, these are our normal feedback linearization terms which we're using, and we're basically having our force control law, which we just derived from the simple spring mass system, we plug that force control law in here and just reflect it in the Jacobian transpose into joint space. So this is exactly our control law which we had, just this super simple F equals whatever it was. I think it was m times x minus x dot plus kp over ke times ef plus f desired. So this is the f you plug in there. It's an end effector space since we're touching the end effector in the world. And for this control law, if you don't care about the acceleration when you're in touch with the world, so if you're approaching my whiteboard, obviously you care about accelerations, but this term doesn't exist since you're not touching anything. The moment you're in touch, you usually don't move anymore so much. So you can ignore accelerations entirely. This is not relevant, so this term will drop out. And all what you do is feedback linearization, u equals c plus g plus that control law. Actually quite simple if you think about it, if you know how to compute these terms. You can do this more complete and compute what the y would be that's shown in the book, but I don't want to go into this details. It's actually not necessary. It's just, you can solve it. Okay, so actually it's very simple now. From our simple 1D math system which we analyzed, we can go plug it into nonlinear system and still do our control as before. So we actually have a reasonably useful force controller. Forget about the y, as I mentioned. Just drop this term, and it's going to work okay. It can do better, but it will work nicely. Small component, of course. That's annoying. When you're touching the world, it's only usually one direction in which you have force control. The other directions you stay in position control. So you now would have to potentially take your task space and say, if I make this here like a sphere, then I have a normal vector here, and I have a tangent plane. In the tangent plane, I do normal position control as we know how to do it. In the normal direction, I do force control. But I can do everything with the Jacobian transpose formulation, remember? So so let's call this here tangent, and I call it T1, and whatever the other direction, which I cannot draw properly. It's on a two-way whiteboard, but this is T2, and this here forms kind of my tangent plane. I don't know how to draw this. But I now can create basically in the tangent plane a control law, which simply creates a force in T1 direction, which is something like x double dot in T1 direction plus x dot in T1 direction plus, yeah, if I need anything else. Sorry, I want to make this a control law. So this would be desired plus k v x in of x T1 desired dot minus x T. This is getting annoying. Plus a p control point x T1 desired minus x T1. Okay, fine. So there would be a PD controller in the tangent space. Okay, so that creates the force in those directions. The same would be in the T2 direction, and in the normal direction we use this force controller. And then we run everything, this three-dimensional force vector, run it through the Jacobian transpose and get it back down. It looks a little complicated, but actually it's very trivial. Okay, we just have our good old friend, a PD controller now in end effector space, and we have a special force control law in tangent space. And now the only thing you have to do is, given that your x, y, z of your end effector will not coincide with this normal and tangent space, you have to have one coordinate rotation between the two of them to relate them to each other. So unfortunately, coordinate transformations matter. Sorry, it's annoying. But these are all the things you have. What is more annoying is actually figuring out, if you do that, what is the normal? Since getting the normal from an object is not so trivial, that usually it has to be done with some kind of visual processing. So how would you do that? Well, these days, all of you know a Kinect sensor. The answer is yes. So a Kinect sensor gives you a point cloud, a 3D point cloud. You know where you want to touch, and you have a bunch. I don't know how to do a point cloud of an object, but then you give you an object. Here's a little cube, and now I create points. Okay, that's the best I can do for you. Did this happen to my computer? Interestingly. Okay. So what you do essentially, you want to touch here, you take a bunch of neighboring points, and what you're going to fit is a linear tangent plane to the data points. It's just a simple 3D linear regression problem. I'll tell you a little bit about linear regression when it comes to adaptive control. But it's super trivial to do. From that, you get at least a noisy estimate of the tangent. Sorry, the normal, or the tangent, whatever you want. You can get both. Obviously, you get both. So the plane is the tangent plane, and what's perpendicular to it is the normal. How do you get the normal from knowing the tangent? Cross product. Okay. Take one tangent vector T1, the other one T2. T1 cross T2 is something which is the normal. You have to normalize it most likely afterwards to make it a unit vector. Okay. An annoying amount of computations in order to do all these things. And then you get noisy normals, and you get a stupid Kinect, which basically puts in some outlier points, and your normal wee goes to this way, and then your robot does wee, something really not so nice. So it becomes more tricky in reality, and the problem with robots in general is it's very different from your standard computer science and Google searches, whatever. If you make a mistake in computing something that you assume is true about the world, and then you act on it, this is bad. Since you can destroy something, or you can destroy the robot, or you can destroy the object you're manipulating, or you can hurt someone. So errors in robotics are much less forgiving than an error in a Google search where instead of showing me the cat, you bring up an elephant. Who cares? Nothing that's, unless, of course, whatever the NSA wants to track the elephant now, right? Fine. Good. Typical example for these kind of hybrid, which is called hybrid control, if you do partially force control and partially position control. There's another word for hybrid control where people mix control tasks which are continuous with control tasks which are discrete. Unfortunately, the same word is used, but right now I just use it for a mixture of position and force control. All of you have seen Karate Kid. Wax on, wax off. That's a perfect task for hybrid control. Position control in the tangential plane, I hope, and force control in the vertical plane, and in the normal direction. Now, last not least, and this is just mentioning that, you can go into the entire story now and do impedance control. This is now when you don't just care about the force, but also the force due to stiffness. We only considered KE here, remember? But you could now also start considering forces which come through viscosity or through inertial forces. And then the control laws just become more complicated. I'm not going to go through them since it's too annoying. You can look in the book. You get control laws essentially which look like our normal inverse dynamics control law. You get your Jacobian transpose. You get your FE here. Then you get somehow inverted inertial matrices in there to make sure that you compensate for what is called the anisotropy of the inertia tensor. Nice word. Okay, very simple. Why this matters is if every object would just be a sphere, we would be so happy. Okay, since that thing has inertia in all directions the same amount. But if it's not, if it's, for instance, an elongated rectangular object, it has different inertia in different directions. And I wish I had a really cool object here. The keyboard would be good, but I shouldn't throw the keyboard. This is in the end a good object. And you can actually test the the main or the minor axis of inertia in this thing, since that's around, it likes to spin. So it usually likes to spin. This is styrofoam. God, I hate styrofoam. But essentially, it likes to spin around this axis very nicely. And I think it would spin around this axis very nicely. It wouldn't like to spin around the other axis. So there's different moments of inertia. And we have an object like this. And if you push it in this direction with a force, let's have a force here, it will not go straight up. It will actually rotate away. If you had a sphere, that doesn't happen. You push the sphere, it will just go straight up. No problem. In this kind of anisotropy, that means the inertia is different in different directions, it gets compensated by putting here the inverted inertia matrix in there, and you can calculate it out. It's a little bit annoying, but it's totally doable, and you get more. This y here, as you can see, becomes a much more complicated term. You get derivatives of Jacobians in there, which are pain. Turns out there is an analytical formula for the derivative of a Jacobian, which looks very similar like our geometric Jacobian. It's just more complicated. Most of the time, you would just take a numerical derivative of this, since it's too much of a pain to get this other thing computed. And then you can basically show the aerodynamics and everything, how it works out. Too complicated, not really what we're going to cover right now. Okay, so that was a quick trip into force control land. Very important. The principles we know from standard control, PD control, get just extended. But then you rethink the process and see what kind of sensors you have, what you have available, what is noisy. You try it out, you get your beatings, go back, fix your control law. But slowly you get into the right ballpark and get a complete control law going, and it's going to work in reality. Again, your physical system, we're always relying right now on models. One of these things, whenever this B-1 pops up, hell may break loose. The inertia matrix is lovely. It's the rigid body inertia matrix. But inverting it may be a pain. It may have bad conditioning because some degrees of freedom are very low mass, some others are heavy mass. And if you have modeling errors in there and you take an inverse of a badly modeled inertia system, it becomes even worse. So there's some very interesting lessons that you can do all these things with simulations and theory, and they're great. And a lot of things don't work in practice at all. They're just terrible. They're not robust towards modeling errors. They're not robust towards noise. So the difference between theoretical and experimental robotics is quite significant. And most people will not accept a interesting theory unless someone shows that it actually works in a practical system as well. All right, that's it for today. Thank you.